just throw them into the chat. It's going to be interactive. I'm going to ask you questions, throw them my way as well. If you just saw Phil's, it was so amazing. I've just been reading back through some of the comments. I don't know how he manages to synthesize so many amazing ideas from you guys during his lives. He's amazing. Anyway, so yeah, today this one is going to be about energy and also power. But before I start, this is actually completely unrelated. But I really just, for some reason, this video that I made just several years ago is stuck in my mind. So I'm just going to show it to you. Here's me, and let me just show you this.
This is just a normal droplet of washing up liquid. Look what happens.
So that's what happens if you take washing up liquid and you drop it into a load of liquid that has got seasoning like pepper, for example, scattered across the top. Who knows why that happens? I mean, it's magic, obviously, but who knows why the magic happens? Shall I show it one more time? I'll show you one more time. It's only 8 seconds. Here we go. Coming up again.
This is just a normal droplet of washing up liquid. Look what happens.
So we got one person saying that the answer is science, which is, of course, a very reasonable thing to say. It is science. Wasn't actually what I was thinking, but yeah. I need to turn this on. Turn it on here. So this is actually not, well, I guess it's physics in the sense that physics describes how the universe works, but this is more chemistry, and maybe if you watch one of Josh's lives, he'll explain to you why that happens. But it's just something that I always find really beautiful, because that little trick is actually the window into beginning to understand how life began in the first place, how the first cells formed, how the first bits of organization of life started to exist. And it all begins with dropping fairy liquid onto a load of water and watching the pepper kind of fly away, which I think is pretty cool. Okay, so I will just say hi to people who are here, because there's loads of people here. Catherine is still here. Catherine, nice. Must be getting pretty late in New Zealand. And Karina is here, and Zanon is here, and Mirs is here, T's here, Laura's here, Jack's here. Hi everyone. Right. Okay, so we'll get started on this one's going to be about energy and also power. So as I said, if you're as I said before, but just to update you, if you're joining late, ask questions whenever you want. We are going to go over the high school physics stuff that you need, ages kind of like 13 to 17-ish. But if you're older than that, it can be like a revision, or if you never learnt it at school, or if it was taught badly at school. And if you're younger than that, don't worry about it. You'll probably get quite a lot of it anyway. But hopefully the concepts will be helpful, and they'll be useful for any kind of like school exams that you have to do these concepts. Right, okay, so to begin with, Smarties, the first scientific question is this. Number 1, which is the best Smartie? The best. Now, I want you to put your answers in, and I want you to do it with a sense of pride, a sense of certainty, and I want you to be sure. Be sure of it, which is the best Smartie. Now, while you're selecting, I am so certain that when I was like 8 or 9 or something, Smarties did a brief window where all the purple Smarties or all the blue Smarties were white chocolate on the inside. And I've tried saying this to several people and no one believes me, but I'm so sure I had a packet of Smarties that like the blue or the purple had white chocolate on the inside, but no one has ever. So if anyone could corroborate that and also has that experience, then let me know, because that would be great. But otherwise, so Rebecca says blue, Jack says brown, Miz says never had the white chocolate Smartie. That's not very helpful, Miz. I'm hoping for someone who has the white Smartie. And the only person and T says blue or brown, it's the only person who's got objectively the right answer here is Laura, because of course the best Smartie is the orange Smartie, because the only one that's different to the others, I don't know if anyone's ever noticed, but orange Smarties actually contain orange flavoured chocolate. It's not that you're just imagining it's orange because of the orange taste, although that is a thing, you know. The things you see have actually quite a big impact on what you think you're tasting, so it is kind of important. Let me just turn that off. But orange Smarties genuinely have orange chocolate in them, and that is why they are the best Smarties. Right, okay, so I wanted to tell you a little bit about energy in relation to Smarties. So energy is something that we think of as being like movement or fire or things like that. But actually, energy is something so fundamental to the universe. It's such a part of the makeup of where we all come from and who we all are and what everything around us is made of. So much so that everything is energy. And this was one of the amazing things that Einstein discovered. And he basically showed us this equation, which I'm sure you all heard of before, which is E equals mc squared, which basically says that anything that is made of anything, so anything that is matter, you just times it by the speed of light squared, and that will give you how much energy there is. So the speed of light is pretty fast. And so you can just take like a tiny bit of matter, times it by the speed of light squared, and that is a lot of energy. So to kind of put this into perspective, if you could take half a Smartie, let's see if we can grab a Smartie, let's grab this green one. You are ours now. Right, let's split this Smartie up into two halves. So let's say that this Smartie here is a normal half a Smartie. Normal and proud. It even has a t-shirt that says those words. And this other side of the Smartie is not a normal Smartie. This other side is made of antimatter. So if you haven't heard of antimatter before, antimatter is just the same as the normal matter or the normal mass that the universe is made from, but it's opposite to it in such a way that when you bring matter and antimatter together, they will annihilate one another and release all of their mass energy, so all the energy that makes up their physical being, and they'll release it in an explosion of light. So like every piece of matter has an antimatter counterpart, so protons, antiprotons, electrons, anti-electrons, and so on. Right, here's the question. What there's a big argument going on about whether Smarties are good or not. Oh, New Zealand Smarties suck. Oh, that's a shame. Yeah, the English Smarties are actually really good, and then the ones in the US, the Hershey's ones or whatever I don't know what they're called, but they're just no, not good times. Total side story. I can't remember if I told this before, but basically, like I went when I was about 6 or 7 years old. I went to the Hershey's factory in America with my brother and sister. And we were like selected to come and do chocolate testing, and we went around the back and we like tested all the different chocolates, and we just had to rank the chocolates that they gave us in order. And I remember being really young and I couldn't really understand why the people who were testing us, who we thought were like these fun people giving us free chocolate, why they kept getting increasingly kind of angry and impatient with us. And it only dawned on me several years later that the reason they were so annoyed with us is because every single one of us consistently put the Hershey's chocolate as the most disgusting chocolate of them all when we ranked it against all the ones they were comparing. And they must have had to have then delivered those results to their managers and been like, turns out the children hate Hershey's chocolate. Anyway, Hershey's chocolate is really bad, in my opinion. Okay, so, right, if you combine a normal Smartie with an antimatter Smartie, then you will get energy released. Now, my question to you guys is, based on how big a Smartie is, how much energy do you think that would be? And I want you to answer in the form of, if you took like a smartphone, like an iPhone or something, and you put it on charge, then my question is, how long could you charge, so how much time could you keep a smartphone charged for by using the energy from taking a normal half a Smartie and an antimatter half a Smartie? How much charge time is that on a standard smartphone? What do you think? Okay, so Zaydon thinks many years, Miz thinks 3 years. Catherine's come in with a huge answer there. Actually, Catherine is the closest by miles. You would be able to charge a smartphone for about 25 billion years with the energy that you could release by combining a normal half a Smartie with an antimatter half Smartie. 25 billion years. That is the crazy amount of energy that is locked up inside all of the matter all around us and all the matter that we are made of. energy completely creates the fabric of the universe around us, and it's a concept that's very weird, and it's something. God, I got something in my throat. Yeah, energy is a very. Maybe it's coming from outside. Oh, close that down. One more. Hopefully that's better. Woo. Energy is a very weird concept. That's something that at school is often taught in quite a matter-of-fact way of like, oh, learn these equations about energy. Energy is quite a simple thing, and it's not. Energy is like so strange and mysterious, and we still have made hardly any progress into understanding what energy really is or where it comes from. Anyway, so this live is about energy and power. This live is about energy and power, and I'm going to start actually by talking about power. So let's go down here, and here are... Oh, she's slightly cut off. Let's move Jacinda down. So here's Jacinda, who's the Prime Minister of New Zealand. And here's me, in cartoon form. Let's drag me up here. Oh, there we go. So, if Jacinda and I both wanted to build a bridge, so let's say we both want to build a bridge, and we want to cover the bridge in trees. And so actually, this is an idea that's already been proposed, and it's called the Garden Bridge, and people were trying to get it built in London. But yeah, if Jacinda and I both wanted to build a garden bridge type thing in the world, then who would have an easier job of doing that? Jacinda or me? Now remember, Jacinda is the Prime Minister of New Zealand. Also, another clue is that Jacinda's second name is Ardern, which is almost garden, if you had a G at the beginning. So that also gives her some element of advantage. Okay, so everyone's voting Jacinda would find it a lot easier to get the bridge built. So the question is why? What is it that Jacinda has that I don't have as much of as she does? I have significantly less than she does. What does she have that would allow her to build this bridge much more easily than me? Catherine says power. Exactly. So she's powerful because she's in a position of responsibility. She's the Prime Minister of the whole country. So Jacinda has this thing which is power. Now, power is not the same as energy. So it's going to take a certain amount of energy to build the bridge, right? And by that, I mean, let's use energy in quite a loose sense here. Let's talk about energy as being like all the effort we're going to have to put into bringing everyone together, getting the resources and so on. So not like the strict definition of energy, but just this idea of like, we've got to build the bridge and that's going to take a certain amount of energy. So ultimately, I reckon if we both committed our entire lives to it, we could both get the bridge built. We could both do it. It's just going to be much easier for Jacinda. So if we both set out trying to build our own bridges, then what is the key difference between the way that between how she manages to build the bridge and how I manage to build the bridge? What is the key physical concept that is different about the way she builds it and the way I build it? And I'm assuming that ultimately over the course of our lives we both managed to get a bridge like this built. What is different about the experience of her building a bridge and me building a bridge? So Zanon's saying taxes would go up. Taxes might have to go up to build a garden bridge, but everyone loves garden bridges, so it might be something that people are okay with on the taxes. I'm actually thinking of something much simpler, like a simple physical concept. I think I'll tell you what it is, because it's one of these things where the question sounds more complicated than the answer. But the answer is just time. It's all about time and the time that it would take. Her bridge will be upside down. That's also an important comment because of the bottom of the world factor. So it's about the time that it would take. So both of us could probably get the energy together to put the bridge in place, but it would take me so much longer than her because I don't have as much power as she has to get things like this done. Whereas she could get the bridge built in a lot less time. So this is the key idea that I want you to think about. Power is all about time. It's all about energy, yes, but it's also all about time. So my question is this. If let's try and work out the equation without just me telling you what it is. So some of you might already know the equation that relates power and energy and so on. But just in case you don't, let's try and work it out. So if you were going to put more energy in, would that mean it would be more power or less power? So more energy means what for the power? That's the first thing I want to know. More energy means what in terms of power. So if you put more energy into something, does that sound like it's getting more powerful or less powerful? And my second question is, if something takes more time, then does that sound like it's more powerful or less powerful? So exactly, people are saying more energy means more powerful. So more energy means more power. What about more time? If there's more time, is that more energy? Oh, sorry, more power or less power? So Jack's coming in, exactly. So more time means less power. So when you're building the equation, you have to think, okay, power is going to be equal to, if energy goes up, then power goes up. So therefore energy is going to be on the top. And if time goes up, power goes down. So therefore we want to divide by time. So we have energy on the top and time on the bottom. So power is the energy per unit of time. Cool. Okay, right. I wonder who knows the answers. These are quite boring questions, but they're ones you kind of have to know for your course. Does anyone know what the unit of energy is? Does anyone know what the unit of time is? And does anyone know what the unit of power is? What do you guys think? Let's see if anyone knows that. And if not, then we'll be able to tell people and we can start to try and remember. Unit of energy. Okay, so Rebecca Carmen's spot on with this. So the unit of energy is joules. The way I remember that is by thinking about what's written on the side of like a cereal packet. Because it'll have calories, but it'll also have joules. And joules is the correct unit for energy. How much energy you get in your food. Time we always do in seconds, which I think is one that people find a bit easier to remember. And then power is joules per second, because it's the energy divided by the seconds. So joules divided by seconds is perfectly reasonable for power. You'll often see it written down like that. However, power also has another unit, which is watts. W, capital W, and if you write it out in full, is W-A-T-T-S. Watts. So power you can give in joules per second or watts, doesn't actually matter. It's the same thing. Right. Okay. So let's ask a quick question on that to make sure that makes sense to everyone. So let's say that I am gonna let's say I'm gonna like burn a fire, and the fire is gonna release 500 joules of energy, and it's gonna release these 500 joules of energy in, let's say, 2 minutes. So it's going to release 500 joules in 2 minutes. What is the power of the fire? What is the power of the fire? So 500 joules in 2 minutes. Now I'm going to start, I'll throw in the answer if you get it quicker, but I'm going to start explaining it. So power is the energy divided by the time. So when you're answering a question in physics, you should always write out the equation first, and then you write it out again, but including the numbers. So power is, and then the energy is 500. Now don't be tricked by the fact I've written 2 minutes. You need to convert that to the right unit, which is seconds. So it's 500 over 120, which I can see some great answers coming in. Let me just move that upwards. Yeah, 500 over 120, which means the power is equal to 4.2 watts. Perfect. Watts is also maybe easy to remember because you often see it on the side of light bulbs. That's how I first started remembering watts. Watts is how powerful a light bulb is. So a powerful light bulb will have a big wattage, and you know that it's going to be a bright light bulb. That was great. Well done. So many people got that right. Okay, let's have another go. Just to do one more of those. Right, if we have, let's say we've got a light bulb and the measurement on the light bulb says it's 0.2 kilowatts. So it's a 0.2 kilowatt light bulb, and we are going to switch this light bulb on for 1 minute. So if we switch this light bulb on for 1 minute, then what is going to be the energy that is released by this light bulb? So again, I'll start writing it out. So you always write to begin with, power equals energy over time, get the equation down, and then let's move this up a bit. So yeah, power equals energy over time. So power is 0.2 kilowatts, which we've got to convert to watts. So that's going to be 200, because a kilowatt is 1,000 watts. So 0.2 of 1,000 is 200. So that's your power. And then the energy we don't know yet, and the time is 1 minute. Again, got to have it in seconds, so we've got to call it 60. So, therefore, the energy, if you rearrange that, watt divided by 60 will give you 200. Someone put it, yeah, so Rebecca, Carmen, and Karina have both put it in. Brilliant, so good, well done, guys. So yeah, 12,000 joules, nice. Yes, the energy released there is 12,000 joules, really good. Okay, right, now let's go over here to this big old bicep that's here. So something that like really, I remember I was training to be a nurse, because one of the first jobs I did was as like a nurse auxiliary, because I wanted to be a doctor, and so I was like doing loads of nurse work, because I really like that idea. I remember hearing about Steven Spielberg, who was like quite a famous director a while ago, and I heard that like when to become a director, he worked all the different jobs. He worked as like an editor, he worked as a producer, he worked as a runner, he even maybe did a bit of acting, I don't know. But anyway, I don't know how much of this is true, but it just really stuck with me, this idea that in order to become the director, like the boss of everything that was going on, he kind of learned about, he experienced all the different roles so that he would never have to kind of look down on people or disrespect people, or and he would never be kind of asking someone to do something without really knowing how much he was putting them through. Anyway, I figured if I was going to be a doctor, not to say that doctors are the bosses of nurses, because that's not how it works, but when I was going to be a doctor, I thought it would be good if I'd like be in as many roles as possible. Anyway, ended up not becoming a doctor because I studied chemistry instead, so it was all just kind of an experience. But ultimately, I was training to be a nurse, and I saw this diagram in this like health and safety meeting I had to go to, which was pretty boring, to be honest. And it had like a muscle and then an arrow pointing to the muscle, explaining that it was moving because energy was going into it. And I remember looking at this and being like, that's not right. There's something weird about this. Like, it's not this idea that energy is given to things and then used up is not how the universe works. Like I was trying to imply before when we were talking about Smarties, and if you missed this bit, just to really quickly recap, half a normal Smartie plus half an antimatter Smartie will release enough energy to power a smartphone for 25 billion years. Anyway, going back, basically, like, energy is part of the fabric of the universe. Everything is made from energy, and everything is like a flow of energy moving from one form to another. It's not that you can put energy into an arm and then the arm will do a thing. It's that energy flows from one thing to another. So I thought that maybe actually we'll come back to this, but let's go to these frogs. And using these frogs, let's talk about some of the different kinds of energy that exist. So can people throw in ideas of like different kinds of energy that there are? So I want to see if people know the ones that are like the things that you're supposed to know for the physics syllabus, because it's a bit of a broad question, this. Okay, Rebecca Carmen is saying kinetic, yes. So kinetic energy is an important one. So for those who don't know, kinetic energy is the kind of like sciencey word for movement energy. I don't know why they don't just call it movement. It's one of those annoying ones. But anyway, kinetic is movement. Yeah, chemical is another. So chemical is the energy that's stored inside chemicals. So if you were to set fire to a piece of wood, then you're basically taking the chemical energy that's stored and you're turning it into, let's see if no one's written that kind of energy yet. Well, you're turning it into thermal energy and also light energy. I'm going to give the yellow frog the thermal energy and the light energy because those are the two of the coolest energies. And the yellow frog deserves some pretty cool energies. Okay, so nuclear is another great one. So that's another one that's like a storage energy. So let's give it to the brown frog. The brown frog can have all these like nice storage energies. Nuclear. Oh, so gravitational potential is great. That's really good. So gravitational potential is literally the energy of like holding this pencil up here. I've stored energy. It's gravitational. It's potential, and potential means it has the potential to fall. So as soon as I let go, all of that energy becomes kinetic energy. It becomes movement energy. But the key idea that you have to get used to is that all of that energy flows from gravitational to kinetic. And then and energy is just a flow from one thing to another. I'm just going to open the window again and risk having a coughing fit again. Oh, so much better. I love it when the window's open. Okay, so let's write here gravitational potential. Can anyone think of any other kinds of potential energy? So like energy that's stored. Gravitational potential. And Xenon's saying that gravitational potential energy can be really high if the object is really, really massive. So if you're right next to a black hole, then you've got loads of gravitational potential energy because there's all that potential for you to fall closer and closer to the hole. So I'm not seeing other ones coming for potential, so I'll just write another couple. So another couple are like magnetic potential, which is like if you hold two magnets close to one another, then if you let go, they might either repel or attract to one another. I'm just going to call it magnetic potential for now. Potential, and also you've got others like electrostatic potential, which would be potential energy, which would be like if you've got two charged objects and they're quite close to one another. And chemical is basically a potential energy as well. Right, so let's look at the energy flows that happen in this arm. So if you're going to move this arm, then what kind of energy are you forming, and where does that energy come from? So what kind of energy are you trying to move towards, and where does that energy come from? I'm going to draw it here. So Xenon's saying it comes from chemical energy. So you've got chemical energy from the sugar that's stored inside your arms. This bicep is absurdly big. It's like it's wider than it is long. Yeah, chemical energy. And what does it become when the arm moves? So you start with chemical, which I'll just label as chemical. And then Laura's spot on and says, Jack, it goes to kinetic energy, exactly. So the kinetic energy is the movement of the arm. Kinetic. This is the arm moving. Now, often what will happen is your body might dedicate to this, let's say 50 joules of kinetic energy. And then the movement energy that you create might actually only be as big as, say, 20 joules. So you might actually only get about 20 joules of kinetic energy out. But the thing is, energy can neither be created nor destroyed. We can't create it, we can just move it from one place to another. This is the thing I was trying to get to before. Like, energy is this very mysterious thing that continuously exists, but we just transfer it from one form to another. So what is the other form? Let's say that this kinetic energy is only 20 joules of energy that you get in moving the arm. Then what is the other form of energy that you might consider to be wasted energy because it's not the energy that you were trying to make? What is this other form of energy that's being wasted? And for those of you who've seen these before or wants to know what they're called, these things are called Sankey Diagrams. They're kind of not really that complicated in the sense that they're just like a nice picture to show the energy splitting up, but they've got a complicated name which some schools and syllabuses want you to remember, but you don't need to remember the name in my opinion, just as long as you know how it works. Okay, so Jack is saying heat, Laura's saying heat as well, perfect. So we're getting a lot of this energy is wasted as heat or thermal energy. So the question is, how much energy is wasted as heat? And hopefully this will be an obvious question, an obvious answer. If we've got 50 joules of energy going in and we've only got 20 joules of kinetic energy coming out, then how much heat energy is being released as well? 30 joules, perfect, yeah, exactly. Good, nice, Xenon. So yes, because energy can neither be created nor destroyed, so the amount of energy that goes in has to be the same as the energy that goes out. Now, my question to you guys is, what is the efficiency of this process? How efficient is it? And by that, I mean, what percentage of the energy that went in ended up coming out as the thing that you wanted. Oh, not efficient, I meant efficiency. So the efficiency equals the useful energy over the total. But I don't think that's an equation that you're often given in schools, but I don't think you really need it if you just think about what it means with 50 joules going in and 20 coming out, and everyone's got bang on 40%, which is perfect, so everyone completely gets this. Nice. So this bicep is 40% efficient. Now, one of the things we're constantly trying to do in the world is make energy processes more efficient, because if we can make energy processes more efficient, we're going to waste less energy. And when I say waste, where does this wasted energy go? So when people talk about energy being wasted in the world, where does it end up? What are the forms of energy that generally carry energy away from the planet? Because our planet obviously only has a finite amount of energy to spend, and the question is how is that energy kind of lost to outer space? Because it can't be destroyed. It just ends up being dissipated, is the word we use, like spreads out thinly over the rest of space. And also, you might think, oh, we're going to run out of energy. But actually, think about that Smartie that I showed you before. There is so much energy in the matter on this planet that ultimately, if we manage to enable technologies where we can kind of unlock the full amount of energy in matter without having to track down antimatter to do it, or I don't know how we'll do it, then there is just huge amounts of energy to spend on this planet. So what are the forms of energy that kind of are energy wasted as it goes into space? No one said, so I'll just say the kinds of energy that are wasted going into space are your heat energy and your light energy, and generally it's actually heat in the form of light. So these are the forms of energy that kind of disappear from the planet off into oblivion and are never seen again by our planet. But thankfully, we've got a constant source of heat and light also radiating onto the planet the whole time, which is the sun, which is why ultimately it's not too much of a worry right now. And the worry is not that we're running out of energy. That's just kind of a lie that's perpetuated by fossil fuel industry people to allow them to put the price of fossil fuels up. We're not running out of energy by any means. We've got so much energy on the planet still to burn through. And I'm not saying that it isn't finite, because obviously it is finite, and like any resource, we should look after it and use it in a reasonably slow way so that we don't completely destroy the biosphere, which we are doing at the moment. But ultimately, the main problem is not that there's all this energy being burnt as such. It's that we're releasing all of these greenhouse gases at the moment. That is the big old problem. Anyway, right, so let's go up here now that you've worked out these different kinds of energy. There's one thing in physics which I think is probably the hardest thing in energy that you'll do. Most people do it around age 15, 16, 17. So if you haven't done this, then don't worry too much about it. It's because it's probably the most complicated bit, but I'll just take you through it anyway. So the equation for kinetic energy, so the amount of energy that something has as it's moving, is this. It's half times the mass of that thing times the velocity squared. So let's say that one of these frogs has a velocity of 5 meters per second, and it weighs 3 kilograms. What is the kinetic energy of this frog as it's speeding along at 5 meters per second and it weighs 3 kilograms? So remember, this is the mass. Oh, that's going to be out of sight, isn't it? Wait, let me move this down a little bit. This is the mass and this is the velocity. And this is the kinetic energy. So Laura is spot on with this, with it being 37.5. So let's just go through the numbers really quickly together. So if the velocity, so the speed that the frog is going, is 5, and the mass is 3 kilograms, then 5 squared is 25, times 3 is 75. Half of that is 37.5. So this frog has 37.5 joules of kinetic energy. Okay, cool. Right, let me just remove those numbers. Now, another kind of equation that you will see quite a bit when you're going through your physics is this one. So this is the equation for gravitational potential energy. So how much energy something has just because it's being held up at a high point. And that is equal to the mass, so how heavy it is in kilograms, times the gravitational field strength, which we were talking about on Monday. So that's how much stuff accelerates in our gravitational field strength. So it's about 10 meters per second every second is how much faster stuff gets on Earth. So I'll just label that as 10 meters per second squared, times the height that it's dropped from. So or the height that it's held at. So if we were to hold this frog here in a kindly non-threatening way at, let's say, 10 meters high, and this frog weighs 4 kilograms, then what would be the gravitational potential energy of this frog? So have a go at doing that. Now again, this is just like before, M is for mass, G is the gravitational field strength, so that's how much something speeds up as it falls through our gravitational field close to the Earth's surface, and H is the height, how high above the ground you are holding this from. So I'm going to give you guys a bit of time for this because I recognise that I'm just throwing two quite big equations at you, and these are actually the two biggest equations that you will really encounter in physics ages like 15 to 16. In age 17 you start to get some bigger equations, but these are probably the most complicated too. Okay, so the gravitational potential energy is going to be the mass, which is 4, times the gravitational field strength, which is 10, times the height, which is also 10. And so it's going to be 4 times 10 times 10, which is 400 joules, which Karina and Zanon have both got spot on. Perfect, great. Okay, so you know how to use those equations now to work out the kinetic energy and the gravitational potential energy. Right, now it's time for the bit that is kind of cool, but also probably, as I said, like one of the hardest bits that you do of your physics at this kind of age. But I'm actually just going to grab this so that we can float it above the rest of stuff over here. In fact, let me get rid of that. Come down here, nuclear. Oops, slightly off. Yeah, this bit's going to be really useful, so I just want to grab it. Oh no, it's going to have that line inside it. Oh, total fail. Sorry guys, I'm absolutely messing this up. There we go. Right, so we grab these two bits, kinetic energy and gravitational potential energy. So let's go over now to this friendly whale. Right, so I'm just going to pop those down there. And in fact, we don't really need the kinetic energy bit from the side, so let's do that. There we go. Right, so this whale, let's say it's dropped from above the ground from a height of, let's say, 5 meters. So if this whale is dropped from 5 meters high, then what speed does it hit the ground? Now, when I was first asked this question, when I was doing my physics the first time, I was like, surely that's not enough information. Like, how can you possibly know the speed that something's going to hit the ground just from the height that it falls from? But if you remember on Monday, what I was talking about, I was saying that actually everything accelerates at the same rate in our gravitational field. I mean, obviously some things like a piece of paper or a feather that have a bit of a weird thing going on because they've got all this air resistance pushing them up because they're so like fluffy and wide. But in general, things all accelerate at the same speed. So actually, just knowing that something's 5 meters above the ground, that should be enough information. And the reason, and this is quite a hard physics question because it requires you to start doing a skill that is something you generally start doing a bit later in physics, but I'm just going to show it to you now. So this works really, this is a really important concept with energy, because what we have to think is that when the whale is above the ground, what kind of energy is stored in the whale? So obviously there's all the chemical energy because the whale is like made from chemicals and it's got all its food inside it and all that kind of stuff. But what is the energy that's stored in the whale because of the fact that it's 5 meters above the ground? What do you think? Jack's got it. Exactly. So this whale has got gravitational potential energy. It's got some amount of gravitational potential energy. Now we know that gravitational potential energy is equal to the mass times the gravitational field strength times the height, but we don't know the mass of the whale because I haven't told you. And so you can't work out the gravitational potential energy. Oh, Laura's got it as well. Perfect. Great. So you can't work out the gravitational potential energy because the whale is because we don't know the mass of the whale. But what we do know is that if we imagine that this is going to be 100% efficient and every single joule of gravitational potential energy is going to turn into another form of energy as it approaches the ground, what is that other form of energy that all the gravitational potential energy is going to turn into at the instant just before it hits the ground? So what kind of energy does it have loads of just before it hits the ground? What do you think? Yeah, and Wilt has got a great... oh, it's Will. Hi, Will. And Jack's got it as well. Kinetic. Perfect. So all of this gravitational potential energy is going to turn into kinetic energy. And this is going to be a perfect transfer. 100% of the gravitational energy is going to turn into kinetic energy. So gravitational before is going to equal kinetic energy after. Now, obviously, when the whale hits the ground, all kinds of other things happen, like sound energy being released, heat energy... blah, blah, blah. We're not going to worry about that. I'm just talking about the instant before the whale hits the ground. So we know that all of this is going to turn into all of this, which means you can just take your equations and say gravitational potential energy is going to equal kinetic energy afterwards. And this is where the magic starts to happen. So, and if anyone manages to start working out the answer before I finish, do throw the answer into the chat because I'm interested to see if anyone's manages to get it really quickly. So gravitational potential energy before equals kinetic energy afterwards. So let's grab this. GPE equals m times g times h. So the mass times the gravitational field strength times the height is going to be equal to the kinetic energy, which is half times the mass times the velocity squared. Now, does anyone notice? So Karina's got it, which is great. Nice work, Karina. Can anyone see what you're supposed to do at this stage? So if you haven't got it, don't worry yet, because this, as I said, is like one of the hardest bits of this bit of physics. What can we do at this stage to make this equation easier? So the thing we want to do is divide both sides by mass, because you're timesing both sides by mass, and you can cancel it out. So we can get rid of mass on this side of the equation, and get rid of mass on this side of the equation. And Rebecca's got it as well. Perfect. Cancel out m. And so you don't need the mass in order to figure out how fast this thing is going to hit the ground. So we know that the gravitational potential we know that the gravitational field strength is 10. We know that the height is 5. We know that this is half, and then we just need to work out v squared. So 10 times 5 is 50, and then times both sides by 2. So, well, let's just write it out just step by step. So 50 equals a half v squared. So that means that 100 equals v squared, which means, as Karina got really fast, which was great, the velocity is equal to 10 meters per second. Perfect. Okay, great. Right, now let's see how much people are following this with. I'm just going to go down here and we'll cover this bit up to begin with because I want to use that. I'm going to show you that in a minute instead of revealing it now. Okay, so let's have one more go at doing something similar to this. So I'm just going to get rid of all this stuff here. And what I'd like you guys to do is tell me how high, if you were to take a piano and you were to fire it out of a cannon upwards, straight up into the air, and you were to fire it upwards at 7 meters per second, then how high would it get? How high would the piano get above the ground? Again, it seems like there's not enough information, but there is. So I'm going to work through it again, but if you want to go ahead and try and do it yourself, then please do and throw your answer into the chat, because again, I'll be impressed if people can do it quickly. So again, if we're firing our piano upwards, then we start out with kinetic energy due to this speed that it's got, and we're going to turn that into gravitational potential energy as it gets to its highest point. So the kinetic energy is half mv squared, just like before. And we're going to turn that into gravitational potential energy, which is mgh. So once again, we can cancel out the mass. And half of v squared equals g times h. So what do you guys think the height it's going to reach is going to be? So again, the velocity, so the speed, is 7 meters per second. And the gravitational field strength of the Earth is, like we were saying before, 10 meters per second, which means, like I said before, that when stuff's falling in the Earth's close to the Earth's surface, it will get 10 meters per second faster every second. All objects, unless they have like loads and loads of air resistance. So, what height are people coming to? I actually haven't worked this out. It's going to be 245. 245. Yeah, great. Okay, so Laura's right, 245 meters, and Xenon is right with 245 meters as well. Brilliant. And I think that Karina, you must have. Oh wait. No. It's not 245 meters. That's meters. Wrong. I've been confused by everyone throwing their answers in. It's 2.45 meters, which is exactly what Karina said. It's 2.45 meters. 2.45 meters. I just made the same error as I was doing it quickly as everyone else. To get the 10 to the other side of the equation, we need to divide both sides by 10. So we're going to do a half times 7 squared. So a half of 49 is going to be 24.5, and then we need to divide by 10 to give us 2.45 meters. Great. Okay, cool. That was really good. I'm glad that people are starting to get a hang of that, because that is one of the toughest areas. Right, now to finish, I just want to show you quickly this kettle, because I thought I'd just quickly talk about different ways that we generate energy around the world. And there are loads of different ways of generating energy. Who knows what kind of energy is what kind of energy is being used here to heat up this kettle? What is going on here? And also, please can everyone, once you've said what the kettle is, I also want you to throw into the chat ideas of different places that we get energy from. I was going to write them out myself, but actually we're approaching the end of the time, so I just want you guys to throw them in. Okay, so Miz is saying solar, exactly, and Catherine is saying reflection. So it is the reflection of light, but this is light energy, and so we call this kind of energy generation solar. So this, when we're talking about energy generation, like how we make it with a power plant or something, we're not talking about this same list as we did with the frogs, like our kinetic, our nuclear, our chemical. These are the physics words we use to describe different kinds of energy. But over here, we're talking about what the world uses to describe ways that energy is generated. And by generated, obviously you can't make or destroy energy. So what I really mean is how energy is taken from some other source and put into a system that we find useful. So yeah, this is an amazing mirror system that's used all across the Himalayas. So I've never been to the Himalayas, but if you ever go there, then you'll find that loads of the local people will heat their kettles by just having these mirrors just sat outside, and the sun will just shine onto the mirror and then just bounce onto the teapot. And so you'll get all of the sunlight focusing on the teapot, and they get incredibly hot very, very quickly. There are also now these huge power plants in, I think they're in Morocco actually, where it's just a tube of water, and the tube of water just runs above a kind of long curvy mirror, and all day the sun is just shining on these mirrors which just focus the light onto the tube of water, and it just heats up the water really, really hot, and then the water is used to generate electricity. And we won't talk about how that is now, but anyway, basically there are loads of different ways we can make electricity. Who can think of some? So Catherine's saying hydroelectric. So hydroelectric is great. Hydroelectric is the one where you build a big dam, you dam up the water, and then you let the water go through a small hole in the dam that will then drive a turbine, and the turbine is like a propeller that we can use to make electricity. in general, we'll do that another time. I think that's another lesson coming up, actually. But basically, if you can make stuff spin, then you can turn it into electricity, which we'll do later. But hydroelectric is this idea of taking water and driving it through a turbine in the bottom of the dam. We used to think this was such a good idea. Hydroelectric used to be such a good idea because we were like, how can there be a cleaner way of generating electricity than just building up the water and then allowing it to flow through a little tunnel at the bottom, and then we allow the river to carry on flowing like that. But just like almost all things when humans interfere with the world on a large scale, so much worse than we thought it was. Hydroelectric is responsible for so much destruction of species because actually there are so many living things in the water that depend on the water being connected from the top of the river to the bottom. We've tried to build these things called salmon ladders, which are supposed to help the salmon kind of climb up the side of a dam, but the salmon don't use them. They hate them. And so like almost all the time, so every single year you have loads of volunteers who go and like try and help the salmon over the top, and they've invented these things called salmon cannons, which they use to kind of like fire the salmon over the top of the dam to try and help them along the way. But it's ridiculous like how much of a problem it is. And then you've got all these problems like sediment kind of not flowing down the river, and like different ecosystems being separated, and that's only the tip of the iceberg, because actually all the stuff that you raise the water loads here, and this is an area of habitat that's normally full of like trees and bushes and all those kinds of things, and what happens to these is that they rot, and as they rot they release a ton of methane, and methane, as many of you will already know, is many times more powerful a greenhouse gas than carbon dioxide. And so dams are actually responsible for vast quantities of methane. So whilst hydroelectric, it generates a huge amount of power, but also it's not just like a magic bullet of clean energy. And that's why my view is that it's good to have a bit of hydroelectric, but not every single river in the world, because that would be a disaster. Especially when it becomes political in certain countries, like dam up the river and then it limits the flow of the river for the next country downstream. Like, this is when it starts to become really crazy. Anyway, so yeah, there's other forms like solar. Solar's really good, especially this kind of solar, because it's so simple. And we're just heating up water. It's very undamaging, that mechanism, and we can use the evaporation of the water to drive turbines. Solar cells, so that's like your kind of black solar panels that directly make electricity. Technology for these is advancing really fast, and that's great. I remember like sitting in a lecture a few years ago and they were saying, oh, it's going to be decades until solar's a big thing, and then suddenly something changed and it must have just become profitable to run solar panels, and then boom, like the whole industry exploded, and then there was suddenly loads of solar panels everywhere, and now they're getting more and more efficient, and solar panels are quite good. A problem with them is that they're made from chemicals that often cause a lot of damage in their extraction, and then there's a question about how do we dispose of old solar panels without it being hugely polluting. So again, not perfect, but it's kind of moving in the right direction. What else is there? Geothermal is an interesting one, where you like take a load of water and you pipe it really deep underground, and then it comes back out of the ground again steaming hot, because under the ground is super hot, and then you can use this hot water to heat up turbines as well. A lot of it's really weird to think about this, but almost all of our electricity generation is based on heating up water and getting the hot water to spin a turbine for us, because as it evaporates, the water vapor rises and that can turn the turbine. Anyway, and then there are other forms of energy which we're not going to go into now, like nuclear energy, where you take you're basically taking mass. It's kind of like Smarties, except instead of combining a matter Smartie with an antimatter Smartie and causing a big huge explosion, instead you just take a small amount of uranium, which is a very heavy element, and you break it up into other materials that are in total almost exactly the same mass, but just slightly lighter. And because they're slightly lighter, this tiny amount of energy, this tiny amount of mass that it's reduced by, converts to energy that we can use. Anyway, and obviously then almost all of the world's energy is still generated from fossil fuels, which is a total disaster. And if properly smart people were running the world, who were actually thinking straight and actually thinking about the bigger picture, then there is no way we would still be living in a world where there's so much burning of fossil fuels, when we are so certain of the science of its extreme danger to all of us. And we live in a totally absurd world that is still allowing this to happen, and is turning the ship that is heading for its collision way too slowly still to avoid the impending collision. And you all know, if you've been watching me before, that my opinion is that we need to do so much more to turn this ship around, to avoid potential climate disaster that is already beginning. So that was a bit of a sad note to leave it on, but it's really important because it is a disaster what's going on at the moment with fossil fuels, and it's ongoing. And of course, we all have to live with it. We will all grow up into this world that has been built by adults who only seem to care about profit and money and have not really properly thought through the reality that we are going to have to inherit until perhaps it's too late, and hopefully is not yet too late. So, sober thought, but anyway, I'll just quickly show you actually what's coming up next so you guys know. So coming up next in 5 minutes is Nish. Nish is going to do how to analyse an argument, which is going to be beautiful. I am not very good at analysing arguments, so again, that's what I'm going to come to. I'm going to all the humanities ones because I am just like, it's labelled as philosophy here, but it's actually just general humanities, so this is applicable for like geography, religious studies, history, philosophy, all those kinds of things. So that's a really, really versatile one. I encourage you all to go to that one if you can. And then tomorrow, I'm going to be back. Oh God, I'm doing all of the things tomorrow. There's no one else. Oh, it's just me tomorrow. I'm doing all of these ones, and come for Sarah Pearson, especially in the afternoon, evening in the UK or wherever that time might be where you are, because that one is going to be amazing. And then on Friday, we got one on music as well from Jazz, which is going to be great. Right, yes, thanks all for coming. Do sign up to our socials, sign up to our schedule, and do give us feedback below the stream if you can. Thanks all. Enjoy Nish in 3 minutes.